When engineers test control systems, they have to analyze how those systems respond to an enormous range of frequencies. But if you try to plot that response on a standard linear graph, you run into an immediate problem. The low-frequency data gets crushed into a tiny sliver on the left, and the high-frequency data stretches endlessly off the page. To understand the solution, think about human hearing. The difference between a whisper and a stadium subwoofer spans factors of millions, but our ears process that pressure logarithmically, turning those extreme ranges into manageable, even steps of perceived volume. Control systems face the exact same reality. A drone's flight controller has to respond to incredibly slow baseline wind disturbances, while simultaneously managing blazing fast high-frequency motor dynamics. This is the canvas that solves the problem. It is a semi-logarithmic graph. Now, using a logarithmic scale on the horizontal axis, every factor of 10, whether it's from 0.1 to 1 or 10 to 100, gets the exact same amount of visual space. Mastering the geometry of this specific grid is how engineers map out extreme frequency ranges. It allows us to predict, entirely on paper, whether a physical system will hold steady under pressure or violently tear itself apart. When you connect physical components together, like a sensor feeding a controller, driving a motor, their individual transfer functions multiply together. Calculating those varying gains by hand across thousands of different frequencies is incredibly tedious. The Bode diagram uses a mathematical shortcut. When magnitude is converted into decibels, or dB, the math changes. Because decibels are ratios, multiplying two components together becomes simple addition. You just stack the decibel values on top of each other. Because we can simply add these pieces together, we don't have to plot complex systems point by point. We can break any system down into standard, predictable building blocks. There are only about 6 base shapes you need to know. Let's look at the integrator. On a Bode plot, an integrator is a steady, straight line dropping at exactly minus 20 decibels every time the frequency increases by a factor of 10, a decade. Its phase angle is entirely locked at a flat minus 90 degrees. Next is the first-order lag. This shape stays completely horizontal, maintaining a gain of 0 dB until it hits a specific break frequency. At that exact point, it abruptly angles downward, matching that same minus 20 dB per decade slope. Think of this break frequency like driving across a perfectly flat plateau. You maintain altitude until the edge, then lock into a steep downhill grade. By learning to recognize and isolate these distinct blocks, the integrators, the lags, the leads, you can sketch the frequency response of a highly complex machine just by adding straight lines together. Let's put this into practice with a 4-step sketching method. We will map a composite system, G of S equals S plus 3, divided by S times S plus 1 times S plus 2. Step 1 is normalization. We rewrite the function to factor out the constants and reveal the baseline DC gain. If you skip this, your entire drawing will start at the wrong vertical altitude on the graph, throwing off all your stability calculations. Step 2 is finding the break frequencies. We look at the terms in our normalized equation to find the corners. Here, we have distinct corners at frequencies of 1, 2, and 3. These are the exact numerical markers where our plotted line will change direction. Step 3 is initialization. We calculate the exact magnitude and phase 1 decade before our first real corner to establish a firm anchor point. Since our first corner is at 1, we calculate values for 0.1 radians per second. This gives us our starting dot at 23.47 dB. Step 4 is building the slope table. We track the accumulating angles as the frequency sweeps forward. Starting from our anchor dot, the single S in our denominator, the integrator, forces our initial line downward at minus 20 dB per decade. We draw that initial slope until the frequency hits exactly 1. Here, our first lag term activates. It drags the slope down an additional 20 dB per decade, bending our line to a steeper minus 40 angle. We follow that trajectory until the frequency hits 2. The second lag term kicks in, stacking another minus 20 downward. The line bends again, accelerating into a minus 60 decibels per decade plunge. Finally, we hit our last corner, at 3. This term is a 0 in our numerator. Zeros do the exact opposite of lags. They pull the line upwards by positive 20 dB per decade. This shallows our slope back out to minus 40 decibels for the remainder of the graph. This four-step stacking method converts advanced calculus into a straight-line drawing exercise, generating a highly accurate map of how the system behaves. Now we use the completed drawing to extract the actual safety margins. We are looking for the limits of physical safety, which live at two specific lines on our graph: 0 decibels of gain and 180 degrees of phase. First, look at the phase plot on the bottom. We find the phase crossover frequency by locating the exact point where our drawn line crosses the absolute limit of 180 degrees. From that exact point, trace straight up to the magnitude graph. The vertical distance from our plot up to the 0 dB line is the gain margin. This measures how much more gain the system can handle before going unstable. Next, we find the gain crossover frequency. This is the spot on the top graph where our magnitude line crosses 0 dB, marking where the system stops amplifying input energy. We mark that point and drop a line straight down to the phase graph. The vertical distance from that new point down to the dangerous 180-degree threshold is the phase margin. As long as both of these measured visual gaps, the gain margin and the phase margin, remain positive numbers, the engineer has mathematical proof that the physical system will remain stable under operational pressure. We took a dense mathematical equation and translated it entirely by hand into a visual map of physical safety limits. Those margins dictate whether a machine moves with perfect precision or shakes itself to pieces. But the Bode diagram is just one way to view this frequency response data. The next step is to take this exact same linear data and bend it into a continuous circle, creating what engineers call a Nyquist plot. Mastering these visual, hand-drawn analytical tools is what translates abstract equations into hardware that stays stable under real-world conditions.